Good afternoon to all and welcome back to ICMPMA 2022. We now move on to the fourth session of ICMPMA and the second session of the day on the topic energy materials. To chair this session, we invite Professor Cyriac Joseph. Dr. Cyriac Joseph took his Master in Physics from Kochi University of Science and Technology and completed doctoral research in the area crystal growth and characterization from Mahatma Gandhi University, Kottayam, and he is at present the Professor and Director of School of Pure and Applied Physics, Mahatma Gandhi University. He's leading an active research group there. The areas of interest span to different fields of material physics, such as organic and inorganic simple crystals, nanostructured materials, magnetic materials, single crystal structure analysis, rare earth-based luminescent materials, etc. 12 scholars have completed their PhD under his supervision, and currently 7 students are associated with him for their doctoral research. He has published more than 150 research publications, contributed to a number of books in his area of research, and thus accredited with an H index of 22. Dear sir, we are honored to have you here with us today. I welcome you to start the session.
Thank you. May I start the proceedings directly?
Yes, sir.
Yes, sir.
So first of all, let me thank the organizers of this International Conference on Materials, Properties, Measurements and Applications, which is arranged in a well-commendable way. I congratulate all the organizers of this conference in various hierarchical levels for their firm leadership. And the first invited talk of this session is by Dr. R.B. Rakhi. And let me give a brief introduction of the speaker. Dr. Rakhi received PhD degree from Indian Institute of Technology, Madras, which is crowned with the Best Thesis Award. Subsequently, she worked as postdoctoral fellow at the Functional Nanomaterials and Device Group of King Abdullah University of Science and Technology. Later, she associated with in the Chemical Science and Technology Division of CSIR NIST. Then moved to Department of Physics, University of Kerala as UGC Assistant Professor. And later she retired to CSIR NIST and now she is the principal scientist there. And it is commendable that she is among the top 2% most cited scientists in various disciplines published by the Elsevier based on the study conducted by Stanford University. And today she is going to deliver a talk on supercapacitors, and I am sure that she will enlighten the participants with her in-depth knowledge in this particular field and hands-on experience. So I invite Dr. Rakhi for the presentation.
Thank you very much, Professor, for your kind words of introduction. I hope I am audible.
Yes.
Okay. First of all, a warm good afternoon to one and all who are present here. And first of all, let me thank the organizers for giving me an opportunity to interact with everyone. So today, I'll be talking about the molybdenum nanostructures based supercapacitors. First of all, let me share my screen. I hope the presentation is visible to everyone.
Yes, but it's not in presentation mode, ma'am.
Yes, yeah. I'm sharing. Is it okay now?
Yes, it's fine now.
Okay. So the title of my today's presentation is Direct Growth of Molybdenum Sulfide Nanowires over Nickel Form Substrates for Supercapacitor Applications. So let me begin my talk with a very brief introduction to the importance of energy storage. See, in the present scenario of depleting energy resources, our modern society is forced to move towards alternative as well as renewable energy resources. But there is an inherent problem associated with all the renewable energy resources like solar energy and wind energy, that they are intermittent. A continuous supply of energy as per your requirement. As when and where you want to use the particular amount of energy, you should have it with you. So there comes the role of energy storage devices. At the forefront of energy storage devices are batteries and supercapacitors. So now let's come to the topic of supercapacitor. Supercapacitor is nothing but an electrochemical energy storage device. It consists of two electrodes which are separated by a separator which is dipped in an electrolyte. This separator needs to be an insulator. At the same time, it should be able to conduct the electrolyte ions. Okay. And when we compare the performance of a supercapacitor with other available energy storage devices, we can see that the supercapacitors bridge the gap between the conventional dielectric capacitors and batteries. That means these are the devices which are having higher energy density than the conventional dielectric capacitors and higher power density than the conventional batteries. And when we talk about the supercapacitor, an ideal supercapacitor should have higher power density and as well as increased energy density, because usually the dielectric capacitors, they will be having very low energy density. So we expect the supercapacitor, it should have intermediate property between that of the dielectric capacitor as well as battery. So it's at the same time, it should possess higher power as well as energy density values. And it should give stable mode of operation as well as safe mode of operation. And there should be low cost production technologies available for the fabrication of the supercapacitors, because the current area currently in the research community is focusing to find out how we can bring out the best out of something by doing in a cheaper way. So cheaper the better. That is the area, that is the direction in the research in the area of supercapacitors. Now, just to give a brief more idea about the supercapacitors. So, based on the charge storage mechanism, the supercapacitors can be broadly classified into two categories, like electric double layer capacitors and pseudo capacitors. Electric double layer capacitor means the two electrodes, they are made up of carbon-based materials, such as either graphene, CNTs, any kind of nanocarbons like mesoporous carbon or even graphite oxide, reduced graphite oxide, the same thing. Okay, all these things can be used as electrode materials in electric double layer capacitor. There, how the charge storage occurs is by there is a electrostatic charge storage between electrode electrolyte interface. Okay, the electrodes, there are, if you remember in the previous slide, I have shown the anatomy of a supercapacitor. It consists of two electrodes separated by a separator dipped in an electrolyte membrane. So these electrodes, they are dipped in some kind of electrolyte. So in between electrode electrolyte interface, electrostatic charge storage occurs. And if the storage is that kind, then we can call it as electric double layer capacitor. There, the electrode material will not take part in any chemical reaction, but surface area of the electrode material plays the crucial role. Because if the electrode material is having maximum surface area, it will be having more charge storage. Now let's consider the other category of the supercapacitors. They are called pseudo capacitors. What is the difference here? So instead of carbon-based electrode, here we are using either transition metal oxides or conducting polymers as the electrode materials. And Here, this in the transition metal oxide, the most popular one was ruthenium oxide because it's a conducting transition metal oxide. But due to the high cost, we have to think about the other alternatives. And then we went to the other things like manganese oxide, tin oxide, iron oxide. Then when we talk about the conducting polymers, PANI, PPY, PE dot, all these things we can use. Here, what happens? There is electric double layer charge storage, that is electrostatic charge storage between electrode and electrolyte interface. In addition to that, the surface layer of the electrode materials in the case of pseudocapacitor, they undergoes surface Faraday reaction when they interact with the electrolyte. Wherever it touches the electrolyte, there it can undergo surface redox reaction. So in that way, it that contribute more charges and more charge storage. So when we compare the performance of EDLC capacitor, as the electrode is not taking part in the chemical reaction, the performance level, it will be very stable. Whereas in the case of, only the electrostatic charge storage is there, so it will be having low capacity. Whereas in the case of pseudocapacitors, there will be surface Faraday layer contribution, reaction contribution is there. So the device will be having more capacitance, but since the electrode is taking part in the electrochemical reaction, the surface corrodes away within the course of time. So it will be having less stability in comparison with that of the electric double layer capacitor. So in the supercapacitor research, people are looking for the hybrid capacitors. Hybrid capacitor in the sense, here we are talking about hybrid supercapacitors with a hybrid electrode material. That is by combining carbon-based materials with a pseudo-capacity material. So we can have high capacitance as well as maximum stability at the same time. Now, before getting into the real topic, we should know a little bit more things. That is, we should know some supercapacitor parameters. First one is called the capacitance. Capacitance, we all know in the school classes, from the school classes onwards, we are learning what is a capacitance of a parallel plate capacitor. That is epsilon A by D, where A is the surface area and D is the distance between the two layers. Two plates, parallel plates. Here, in the case of supercapacitor, here A is nanomaterial, so maximum surface area, and D is the separation between electrode, electrolyte interface. Okay, and then the capacitance is mainly the property which depends on the nature of the electrode material. We should choose the electrode material in such a way that the electrode material should offer maximum good conductivity, maximum surface area with excellent electrolyte accessibility, because charge storage is occurring at electrode-electrolyte interface. So it should have maximum surface area. Either we should play with the morphology or surface area of the electrode material. So for example, you are working with a particular shape of carbon, we should make it in such a way that it should give a morphology which offers the maximum surface area, or we should engineer the electrode itself, the electrode as such, that is electrode material, while it is converted into the electrode material, the surface area property may be lost. So we have to retain. So we should do some electrode design engineering also we should do. Then next one is that the final one is that electrode material should be of a low cost. That is advisable and desirable quality. But sometimes, lab purpose, we will be looking for the materials which offer maximum surface area, good conductivity, and good electrolyte accessibility. If you want to have low cost, we have to stick with the old the mesoporous carbon, manganese oxide, and iron oxide or copper oxide, such oxides. So if you, for a research purpose, we can work on all other transition metal oxide. Now, the other important parameter of the supercapacitor, we already said that the supercapacitor should have high energy as well as power density value. Energy density is nothing but half CV square. C is the device capacitance and V is the potential window. And then the maximum power density means P equals E by delta T. Delta T is the discharge time. And one more thing I wanted to mention here is that supercapacitor is a device which can be charged as well as discharged within fraction of seconds. Okay, within 1 or 2 seconds. Now, the energy density, half CV square, we know that C is a parameter which is associated with the electrode material or the electrode structure, whereas V is the property which is associated with the electrolyte. An excellent electrolyte should have good ionic conductivity, wide potential window, high stability, and less toxicity. Lab scale purpose, we usually use water-based electrolytes for the initial testing, but water-based aqueous electrolytes are having a problem is that it will be having, I think someone else is also controlling this one, the presentation. Okay. For a lab scale electrolyte, we are using water-based system. There the potential window is limited to 1.2 volt, whereas in the case of we can go for organic electrolytes, we can extend the potential window up to 2 or 3 volts. And if you want to have ionic conductors, if you are using ionic electrolytes, we can extend the potential window up to 4 to 5 or up to 6 volt. We can extend the potential window. But for lab scale applications and the initial level of testing, we used to stick with the water-based electrolyte system. So this is the background about supercapacitor, and we found that the electrode material should be having maximum surface area. So we should go for the nanomaterials. Nanomaterials, you know that they are 0-dimensional, 1-dimensional, and 2-dimensional. And in today's talk, I'll be focusing on the 2-dimensional nanomaterial. In that one particular category, MOS2 I have told. So when we consider the 2-dimensional nanomaterials, we can see that there are a variety of nanomaterials with the maximum surface to volume ratio. There, graphene is there, MOF is there, boron nitrates are there, then COF is there, transition metal chalcogenides are there, layered double hydroxides are there, then transition metal oxides, some kind are there, then MXenes are there. So the variety, various classes of 2D nanomaterials are there, but in today's talk, we'll be focusing on TMDs. What is the peculiarity? People have been studying. I have been working in the area of this supercapacitors for nearly more than 2 decades. Nearly 2 decades I have been working in this area. So we have been working also on a carbon-based material, then oxides, then conducting polymers. Then in past 3-4 years, TMDs, everybody is working. What is the peculiarity of this TMDs? Actually, transition metal chalcogenides, maybe most of you know, these are 2D materials with similarities with graphene in their structure as well as electronic properties. These materials are with MX2 stoichiometry, where M represents a transition metal from group 4 to group 7 in the periodic table. That is, M can be either molybdenum, tungsten, or titanium. All these things can be M. And X refers to a chalcogen, such as sulfur, selenium, tellurium, all those things. Till date, more than 60 TMDs were identified, and in that 40 of them are having layered structure. If they are having layered structure, they can have maximum surface area and excellent electronic properties. Okay, and these layers of TMDs are stacked together by weak van der Waals force of attraction, and molybdenum and sulfur, like a transition metal and chalcogen, are bonded together by strong covalent bonds. Among various TMDs, the most popular one is MOS2. That's why in today's talk, we are focusing on MOS2. In that itself, one particular aspect we are focusing on. And if we look into the structure of molybdenum sulfide, we can say that the structure of a monolayer of MOS2 is a 3-atom thick layer in which one transition metal, that is the molybdenum atom, is sandwiched between 2 sulfur atoms. Okay. To a sulfur atom. Based on the coordination between molybdenum and sulfur in a single layer, MOS2 can exist in 3 polytypes. First one is the monolayer tetragonal structure. Second one, hexagonal structure and a rhombohedral structure. This in which the monolayer tetragonal structure is very hard to make it, and this is conducting in nature, whereas 2H and 3R are semiconducting in nature, but these are the stable forms of MOS2 found in nature, hexagonal and rhombohedral structure. And when you consider a bulk MOS2, we can say that bulk MOS2 is an indirect band gap semiconductor with a band gap of 1.23 electron volt. And it can be tuned to a direct band gap semiconductor of like a 1.9 electron volt by making this monolayer tetragonal structure of that is 1D MOS2. And when we look into the properties of MOS2, we can say that these are exceptionally strong. These are scalability for production is there, chemically and thermally stable, and it is lightweight and high surface to volume ratio. That is obvious because it is a two-dimensional structure, as well as high theoretical capacity. So all these things makes it a suitable material for electrochemical energy storage application. So we wanted to explore the electrochemical energy storage properties of MOS2. Now, when we talk about MOS2 in particular, MOS2 can be prepared by different methods. That is either by top-down approach or a bottom-up approach. Top-down approach means we can take the bulk MOS2. We can commercially purchase this one bulk, multi-layer MOS2 we can purchase. Then by some chemical exfoliation or scotch tape method or ball milling, we can separate the individual layer. By scotch tape, we can separate a single layer, but by sonication and all some few layer MOS2, like few layer graphene, we can separate out different layers of MOS2. And so that is one approach. Second one is the bottom-up approach. That is from the raw materials by chemical synthesis, some wet chemical synthesis, we can prepare the MOS2. So let's see the performance of the MOS2 prepared by the top-down approach. That is, it is not as much functionalized as the bottom-up approach. So the properties also differ. When we think about supercapacitors, the supercapacitor performance is better when there are more defects in the material itself. There should be more functional group, then there will be more surface periodic reactions will be taking place. So let's see what will happen. So what we have done is that we have commercially purchased some MOS2 chunks, and then we have subjected into solvent ultrasonication. Okay, ultrasonication for 8 hours, and finally we found that there's some powders from the bulk. We could obtain some powders, and anyway. So as prepared, this one was 2H hexagonal system of MOS2 with the hexagonal phase of MOS2 with the space group of P63 bar MMC. So after ultrasonication, whatever powder we have collected, we have done it's a XRD analysis, the same thing. There will not be any change. And then we have done the AFM to find out the number of layers in this particular different flakes of MOS2 we found that average number of layers were nearly 4 layers were there. Then we have done the surface morphological as well as microstructural analysis. Morphology, it gives some flakes of MOS2, we could find it. And from TEM microstructural analysis, we could find out that the MOS2, these are the sheet form, and it is some few layer MOS2 are there, 3 to 4 layers MOS2 we could achieve. Then, so in any supercapacitor measurement, what we have to do is that we have to first make the material. Then using the material, we should fabricate the supercapacitor. So in the conventional way of supercapacitor fabrication, we have done that. So for that, what we have to do that, if you look at the screen, you can see these 2 black pieces. So these are the electrodes. What we have done that we have mixed the MOS2 with a particular binder, PTFE binder, and then made a slurry and it coated on this current collector substrate. The current collector substrate we used was carbon. Then all these things were, and this is a polymer separator, and entire thing was arranged inside a coin cell assembly, and 1 molar of KOH was used as electrolyte. Then we made so many coin cells. And when we talk about the supercapacitor measurements, two important measurements are cyclic voltammetric measurements and galvanostatic charge discharge, which are shown on the right hand side. A and B shows the cyclic voltammogram. For an ideal supercapacitor, we should get a rectangular. For a perfectly EDLC type of supercapacitor, we should get a rectangle in the CV curve. But in the real case, there will be deviation. It will be quasi-rectangular or shape. And then for galvanostatic, excuse me, for galvanostatic charge discharge, if it is a perfect supercapacitor, ideal EDLC capacitor, we are expected to get a triangular shape, but in the actual case, we will get a it will not be perfectly triangular. Then after we used to make the capacitor cell, then we used to do the electrochemical measurement. Then from the electrochemical measurement, we used to calculate the specific capacitance. Specific capacitance is not the device capacitance. It is actually the capacitance per unit mass of the material using this formula, where M is the mass of the electrode, I is the average cathodic current in this cyclic voltammetric, and S is the scan rate. The other case, but in the when we report, we have to take the capacity measurements from charge discharge measurement using this particular formula, where delta V by delta T is the slope of the discharge curve. Okay, that is the theory. Now, what happened in the real device? So we made the electrode material by exfoliation method, and we have fabricated the supercapacitors, and these are the supercapacitor measurements which we have got. These are the CV measurements and CD measurement. We can see that these are not completely rectangular, but these are quasi-rectangular, and similarly, it is not completely triangular shape of GCD curve. From GCD and CV curve, CSP values were calculated as 21 farad per gram and 13 farad per gram, but we should report only 13 farad per gram because the capacitance value calculated at 1 ampere per gram only we should use for reporting. So this value, when we compare with the other devices, that is very, very small. And then we have compared, we have done other supercapacitor measurements like impedance spectroscopy to find out the RCT, that is the charge transfer resistance value, which we got was quite high. It was 44 ohms. It's too high for a supercapacitor device. Then we have found out the energy density, power density plot, which is known as the Dragon plot, and stability, cyclic stability, only 86% after 5,000 cycles. It is not an advisable value or desirable value for a supercapacitor. So we found out that this top-down approach won't work. It is not as good as any other state-of-the-art material. We can compare it with the performance of a graphene. Okay, so graphene, when we make by RGO, maybe just before this one talk by Dr. Biju was there. So I am not sure how much value he has reported, but usually if you a perfect RGO sample, when we do the supercapacitor measurement at a current density of 1 ampere per gram, we should get something around 150 to 200 farad per gram of specific capacitance per 1 to 2 milligram per of active material. But see, for the same active material, we are getting only 13 farad per gram for a MOS sample. So this is not useful. Why should I work on this material? So we didn't want to leave the topic. So we started preparing this one by other. From our previous experiences, we found that there are different ways. That is bottom-up approach is there. Then we will get functionalized MOS to sample. And second one is that there is another option called direct growth. Then we can avoid the ancillary binders, which are giving the negative effect of resistive effect. So we wanted to remove all those things. So we wanted to perform the direct growth of MOS to nanostructures over nickel from. So this is a condition. What we have done is that we have cleaned the nickel form substrate of area 1 centimeter and the square, and we put inside the autoclave solution at a pH 4 solution containing all the reactive materials like sodium molybdate, then sodium silicate, thiourea, and DI water, and subjected it to the hydrothermal reaction. And hydrothermal growth was performed at a temperature of 180 degree Celsius, and growth time was, we have done it for different growth time. That is also from our previous experience that with other samples, we know that the growth temperature and growth time plays a major role in determining the morphology as well as the electrochemical performance of any material. Then we did in two different ways. We collected all the samples after hydrothermal growth. So on the three-dimensional substrate, we were directly grown these MOS2 nanostructures at a different growth time. And in each case, we collected the growth, the sample grown on the nickel form substrate, as well as there was some deposit in the autoclave itself. That is without any substrate. The sample which was reacted at MOS2 nanostructures formed inside that also we have collected, and we characterize the sample. Here again, all the samples where crystallographic structure were having hexagonal MOS2 with a space group of p63 per mmC. Then what is the difference between the different growth conditioned sample? So these are the sample grown over the nickel form, and when we zoom in, we can see like this. This is by SEM analysis. We have analyzed the morphology of the sample. After 12 hours, nanospheres are present on the surface of the nickel form substrate. When the reaction time is increased to 24 hours, the spheres got flattened and this on the surface of the nickel form. And then the short nanospheres started to emerge at 24 hours itself. At 36 hours, we can see that a brush-type morphology with the perfect nanowires are there. Then what is happening? The nanowire morphology is collapsing at 48 hours. So again, there are entangled nanowires are there. Okay, let's see the microstructure. So from this, from our experience and whatever I have told, you should also have an intuition that the structure which should be capable of holding maximum electrolyte, that will be giving maximum performance. Okay, so out of this, in my, we cannot predict which surface will hold maximum electrolyte. Okay, now then we have done the microstructural analysis by doing the TA measurements, and cross-sectional images of the samples were taken, and we could find that the nanowires are in fact nanotubular form of wires are there. Initially, nanowires that even though we know that the spherical particle, these are the tip of some nanowires. Then we have done the surface area measurements. We found that almost all the samples are having a small BET surface, mesoporous surface area, and the sample which is grown at 36 meters square per gram is having maximum surface area, that is 18.45 meters square per gram. Then what we have done, we didn't test the as-grown like a nickel form sample directly. What we have done is that first, the sample with the maximum surface area, which we expect that which will give the maximum supercapacitor performance, we have constructed the symmetric supercapacitor the conventional way with that particular sample with a mass loading of 1 milligram per centimeter square. We got CV, CD, curves like this, and the capacitance value calculated was nearly 200 farad per gram. So, okay, we can confirm that, okay, this graphene also we used like that only. We used to take graphene, the conventional way only we make electrode and test it. So the performance, okay, the system gives the performance matching with that of the graphene. So I can proceed with this one. So I am confident. Now I am going to, and then we check the power density and energy density, then stability. Stability for the collected deposit was more than 92%. Then what we did that we have gone for fabricating symmetric supercapacitors on with the MOS2 nanostructures directly grown over nickel form substrate. But there we encountered another problem. Here, the lab scale testing we used to test between less than 4 milligram of the active material per liter. From the previous study for testing, I have done with 1 milligram of the active material. But here we found that each electrode was having a mass loading more than 30 milligram. So what is meant by 30 milligram? Above, anything above 10 milligram can be considered as a commercial level capacitor, commercial, industrial or commercial level supercapacitor. Okay, for mass loading per active material per electrode is about 10 milligram. It delivers sufficient energy for the practical application, as well as even if you fabricate in the conventional way also, if you retain your active material mass about 10 milligram, you can avoid the negative contribution from the current collector as well as the binder in the overall device capacity. But there are some, but with the conventional way, if you go for the commercial level capacitor making, that is just by making a slurry, pasting, coating on substrate and using, there are some challenges associated with that. These are the electrolyte diffusion will be very slow and there will be moderate electrical conductivity. Only if the top level is exposed, the other levels are not exposed, it can be brittle. So no mechanical stability, poor specific capacitance, because if you want to know more about supercapacitor, you should read a paper on best practices of supercapacitors by Stoller, which is published in Energy and Environmental Science. It clearly tells why it is happening. When you increase the mass loading, the capacitance value decreases. Okay, specific capacitance drops very much. And then rate capability also reduces. That is capacitance variation with the increasing current density increases, then cycle life also decreases. So these are the well-known problems associated with the commercial level supercapacitor made in the conventional way. So let's see with our material whether we are able to overcome this. So we have a fabricated symmetric supercapacitor with the sample, 12-hour sample, 24-hour sample, 36-hour sample, 48-hour sample. All these things just with the nickel foam substrate directly grown. We are just pasting it and with the help of electrolyte and just taking the connection out and testing. And we found that with the mass loading of 30 milligram per centimeter square, it gave a specific capacitance near to 250 farad per gram. That is a lab scale testing conventional device. Whatever it is giving, that much capacitance we could obtain with this much high mass loading. Then we have done the measurement, the galvanostatic charge discharge measurement. By the way, I didn't mention what is the energy storage mechanism involved here. It is actually a combination of EDLC charge storage as well as very fast surface redox reaction. Okay, but see the capacitance curves. This is almost triangular shapes. And here also we could get a matching performance from the CV and CD measurements. Okay, nearly 250. That capacitance which is occurring at 1 ampere per gram of current density we used to report. And this is here also it is 250 watt-hour per gram. Then what we have done is that we have performed the impedance measurements. I'm not going into the details of these things. And we found that the sample grown at 36 hours gave the lowest RCT. I'm not going to the details of RCT, RS value. RS value is the solution resistance value. It's a property of the electrolyte. If we are using 2 molar KOH, it should be more or less same for everything. RCT is the conductivity of the electrolyte. That is also RCT has been considerably decreased as compared to the conventional way by sonochemical synthesis as well. Then we have drawn the diagram plot and we found that at a constant power density of 0.6 kilowatt per kilogram, our sample gave 12 watt-hour per kilogram, which is equivalent. It is comparable with any state-of-the-art commercial level supercapacitor. So this material gives that, right? It delivers its performance. And so that is the direct growth. In the direct growth, each electrode material is having direct contact with the conducting electrode material. So there is a conduction pathway is there, lowering the resistance, and that 3D structure of the nickel foam offers maximum electrolyte accessibility, maximum exposure to the MOS to nanowires, and maximum capacity contribution. And one more thing I want to add, I have reduced the contribution from the pure nickel foam from all these calculations. So you don't have to worry about the contribution of nickel foam, which was very small. Then we have done to perform the cycling stability. We found that the 36-hour our grown sample gave the stability of 92% after 9,000 cycles, not 5,000 cycles. So it is pretty good, stable, and it is an excellent one. So I would like to conclude by talking about this one, that both the electrode morphology and electrolyte accessibility plays a crucial role in determining the energy storage performance of the supercapacitor. And in this particular study, direct growth of MOS2 nanostructure over nickel form gives the maximum capacity performance. And otherwise, I can say that in any material, whichever material if you take, if you are have a three-dimensional conductive collector, or that if you grow it directly, that is the best electrode material for for that particular material and for the supercapacitor application. This is in fact the first report on MOS2 symmetric supercapacitor with a commercial level mass loading, and it gave a specific capacitance of nearly 240 farad per gram at 1 ampere per gram with a mass loading of 30 milliamp gram per electrode. That is important thing. And the maximum energy density value 12 watt-hour per kilogram, and the cycling stability of 92,000 over 9,000 seconds. Now, I would like to acknowledge the support from CSIR, then DST and SERB through some projects, and University of Kerala for all the support they offered for my students as well as myself during my stay there and now also. And I'm thankful to all my national as well as international collaborators and throughout my career, and now also present collaborator also. And thank you all for your attention. Thank you. Thank you so much. Hello. Hello.
Now the session is open for discussion. Does the audience requires any clarifications?
I think nobody followed anything, or it was too basic that everybody knows it already.
Yes, Praveen raised a question.
Okay. What kV you are using for TEM measurements? I think 200 kV. What 2 kV? 1 second.
Dr. Raki, is it 200 kV?
Yeah. Let me check. I have to check, sir. That I have to check actually.
Okay. Yes, one question from Shailesh. What is the importance of nickel foam?
Sure. We can use some other material like a carbon cloth you can take, carbon fabric you can take, even any fabric you can take and coat it with some conducting material and use it as a substrate. And also stainless steel you can take, copper foil, aluminum foil, any conducting material you can use as current collector.
Okay, Dr. Raki, for the benefit of audience, let me ask one or two questions.
Yes, sir.
What is the significance of that Ragon plot?
What is the significance of what, sir?
Ragon plot.
Ragon plot. With that, we will get an idea where our material stands in comparison with the other electrochemical energy storage devices. How much energy and power, because ultimately in an energy storage device should have maximum energy as well as power density. So where it comes between that these two things, like energy density values and power.
Is it directly related to the commercial application or manufacturing of this as a supercapacitor, this Ragon plot?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir. Comparison between the Ragon plot of your material and
yes, sir. In our manuscripts we have done. Always we used to compare.
Then one more simple question.
Yes, sir.
See, can you differentiate the applicability of this molybdenum and tungsten, W and MO?
Tungsten we can use as electrochromic supercapacitors also we can make from tungsten. And as compared to molybdenum sulfide, we recently started working on tungsten sulfides also. And we get better performance and more conductivity with those systems.
Better performance for tungsten.
Tungsten we are getting recently.
Is there a similar works on tungsten selenide or sulfide?
Yes, recently, yes, they are there. Sulfides and selenide both are there, sir. And also when we want to work with the tungsten, the problem is that we have to go for very high temperature. These things like in hydrothermal itself, we can make it within 180 degrees C or less than that. Even 120 to 180, we can make a molybdenum sulfide. Whereas if you want to have a pure piece of tungsten sulfide or this one, we have to go play with around 225 or 250 degrees Celsius. Above that only it will be formed.
Okay. So that is the limitation.
Yes, that is a limitation.
Regarding the AFM plots,
Yeah.
can you just show that AFM plot? AFM
Yes,
plot.
sir. Okay. Yes. Yes, sir.
So it's a 4-layer system. Okay.
Yes.
Okay. I once again request the audience to clarify if you have some doubts.
Otherwise, they can contact me through email also.
Okay.
Okay, that's fine.
So thank you, Dr. Ragi, for the nice, but I should say very informative presentation,
Thank you, sir.
detailing all theoretical and experimental aspects of work on supercapacitors. On behalf of the organizers and participants, I extend sincere thanks to you. Thank you.
Thank you, sir. Thank you very much.
Thank you, sir. I offer my sincere thanks to Dr. Raki RB for the wonderful presentation. Now we will be having 3 parallel sessions of oral presentations on the topic photonic materials and devices, biomaterials and other materials. All the presenters and participants attending the session on the topic other materials, please continue in this meeting. Those attending the sessions on the topic photonic materials and devices and biomaterials, please visit the link available on the program schedule provided to attend your respective sessions. Before leaving, please fill the feedback form available on the chat box. Once again, if you are attending the oral presentations on the topic other materials, please remain on this meeting. Thank you all. Now we start the oral presentations on the topic other materials. The session will be chaired by Professor Cyriac Joseph. Sir, you may continue the talk.
Thank you. Let us start. The first oral presentation is by Muhsina Taj. So, Muhsina Taj, please start your presentation.
Yes, sir. Good afternoon, everyone. Sir, am I audible? Hello?
Yes, you are audible.
Okay. Good afternoon, everyone. First of all, I would like to thank organizers ICMPMA for giving me an opportunity to present my work. I am Muhsina Taj, research scholar, working under the guidance of Dr. S.R. Manohara, Associate Professor, Department of Physics, Sitaganga Institute of Technology, Tumakuru, Karnataka. My presentation is about enhanced electromagnetic interference shielding properties of p-dot graphene nanocomposites. My presentation includes introduction, nanocomposite preparation, results and discussion, in conclusions. Polymer, which we are well known and using in our day-to-day applications and we know polymer for its good insulating properties. But the 3 collaborating scientists, Alan J. Hager, Alan J. McDermott, and Hirike Shokua, they changed our view and showed that polymers can also be made conductive. For this discovery, they were awarded with the Nobel Prize in the year 2000. There are different kinds of conducting polymers are available. Among those, we have considered poly-3,4-ethylene dioxythiophene for the present study due to its excellent properties like small band gap, high conductivity, greater chemical and thermal stability, fast electrochemical switching, and other properties. We can still more enhance the properties of poly-3,4-ethylene dioxythiophene by reinforcing with a nanomaterial, and different types of nanomaterials are available. Among those, we have considered graphene due to its excellent properties. That is, it is 300 times stronger than the steel, it is stiffer than the diamond, and its thermal conductivity is better than the diamond, and its intrinsic carrier mobility is 100 times more than the silicon. And we have studied the electromagnetic interference shielding properties of the p-type graphene nanocomposites. Electromagnetic interference is nothing but the process by which disruptive electromagnetic energy is transmitted from one electronic device to other. It can be through radiation or conduction. There are different sources of electromagnetic interference, that is radios, televisions, motors, household electronic appliances, etc. And to solve this issue, we can suppress the electromagnetic interference that can be done either by reflection, absorption, or multiple reflection of electromagnetic radiation by using a shielding material. By shielding the electronic appliances from electromagnetic interference, we can enhance the lifetime of electronic appliances and also save our Mother Earth from e-waste. There is an advantage of using conducting polymer nanocomposites to shield electromagnetic interference. That is, they possess both the properties of metals and plastics. We have synthesized p-type graphene nanocomposites by using in situ oxidative polymerization method. And we have studied the Fourier transform infrared spectra of the synthesized nanocomposite in the 500 to 4000 wave number range. In case of pure p-type and nanocomposites, there is a peak around 890 per centimeter in case of monomer E-dot, that is due to CH bond bending. This peak has disappeared in case of pure P-dot and also nanocomposites, indicating the successful formation of polymer. And also the characteristic peaks of P-dot was also observed in the composites, but with a slight shift in the peaks, indicating the strong cooperative interaction between the polymer and the graphene nanoplatelets. We have studied the X-ray diffraction patterns of the prepared samples in the angular range of 10 to 60 degree. For pure p-dot, we have observed a peak around 25.4 degree. For graphene nanoplatelets, it is observed around 26.4 degree. As we keep on increasing the graphene concentration, the peak has become sharp and intense, indicating the periodic monodistribution among the polymer backbone chains. This alternate arrangement supports the charge carrier transport and enhancement in the properties. Some images of the pure p-dot and composites were taken. This image A shows the same image of pure p-dot. Irregular shaped particles were observed, and in the same image of graphene nanoplatelets, we have observed platelet-like structures. When we increased the concentration of graphene to 15% we observed that these platelets-like structures are covered with the irregular shaped particles. This results in an increase in distance between the platelets. This may cause the reduction in the van der Waals force between the platelets and hence reduction in the agglomeration and the better dispersion of platelets in the composite. Thermal stability of the composites was studied in the room temperature to 900 degrees Celsius range. We observed that as we increase the concentration of graphene nanoplatelets, stability has increased. Graphene nanoplatelets have acted as a barrier and helped the polymer chains from getting degraded. They have reduced degradation of the polymer has decreased with the addition of graphene nanoplatelets. We have studied the electromagnetic interference shielding properties of the prepared samples in the 8 to 10 gigahertz frequency range, that is in the X-band range. We have observed that as we increase the concentration of graphene, the electromagnetic interference shielding effectiveness has increased. As we increase the concentration of graphene, conducting network will be formed inside the composite, and also the interaction between the conducting filler graphene and the incident electromagnetic radiation has resulted in the enhanced electromagnetic shielding effectiveness. We have shown here in this graph the contribution of reflection and absorption loss to the shielding effectiveness. It is observed that contribution of absorption loss is more to the total shielding effectiveness. As we increase the concentration of conducting filler, the conducting network formed will help the motion of free charge carriers and contribute to the total shielding effectiveness in terms of absorption loss and reflection loss. Generally, the grading values of electromagnetic shielding effectiveness are tabulated here. If the shielding effectiveness is greater than 10 dB, the material can attenuate more than 90% of the incident electromagnetic radiation. And we have obtained around 17.6, that is around 18 dB of shielding effectiveness for the material that is PDOT with the 15% of graphene nanoplatelets. This indicates that the material can attenuate more than 90% of the incident electromagnetic radiation. We have successfully prepared PDOT graphene nanocomposite using in situ chemical oxidative polymerization method. Using FTR and XRT studies, we confirmed the formation of PDOT graphene nanocomposite. Same images indicated the homogeneous dispersion of the graphene nanoplatelets on the surface of PDOT. And the thermal stability of the PDOT graphene nanocomposites has increased with increase in the concentration of graphene nanoplatelets. And we have obtained a nearly 18 dB of shielding effectiveness. This indicates that material can attenuate 90% of the incident electromagnetic radiation. Thank you.
Thank you, Muhsina.
Yes, sir.
Now, audience can ask some questions. If not, Muhsina,
Yes, sir.
you mentioned that the thermal stability is increased by what factor? I don't remember, but the thermal stability increased, isn't
Yes,
it?
sir. Yes, sir.
Up to what range?
Sir, I will show. Sir, here I have shown the initial degradation temperature of pure PDOT was 200 degrees Celsius. But when we increase the graphene content to 15%, it increased to 240 degrees Celsius in initial degradation temperature. And also 95% of degradation in case of pure PDOT is around 572 degrees Celsius. It increased to 825 degrees Celsius. Sir.
Okay.
Yes.
So thank you, Muhsina.
Thank you, sir.
Thank you.
Yes.
Then Gingermall Matthew.
Yes, sir.
Gingermall Matthew, you can start your presentation.
Yeah, okay, sir. Can you see the slide, sir?
Yes.
Good afternoon, everyone. I am Gingermore Matthew. The topic of my presentation is theoretical investigation on the formation mechanism of N-nitroso-dimethyl amine from the oscillation of acetaldehyde dimethyl hydrazine. Hello, sir. Hello, can you hear me? Hello.
Cyril, sir, I think you are in mute. Can you please unmute your mic and speak? Jindamol, you are audible.
Yeah,
Just wait for Sirix sir to tell.
Jindimol,
yes, sir. Can I continue?
I think there is some issue, whether it is from my side, I don't know.
Sir, can I continue?
Yes, continue.
Yeah, okay. As we all know, the hydrazine and its alkyl derivatives like MMH, monomethyl hydrazine, and UDMH, unsymmetric dimethyl hydrazine, which are high energy fuel and which is used as rocket propellant. The hydrazines are themselves hazardous to human, especially the UDMH, which possess mutagenic and carcinogenic properties. Important oxidative transformation product of UDMH. The NDMA, which is the main oxidative transformation product, N-nitroso-dimethylamine, which is highly carcinogenic. The UDMH and its oxidative transformation products are found to be the important precursor for the formation of NDMA. The ADMH, acetaldehyde dimethyl hydrazine, which give 85% of NDMA during ozonation. Objective of this work is understanding the reaction mechanism, thermochemistry, and predict molecular geometry of the reaction which involved in the formation of NDMA from ADMH during ozonation. Computational methodology. The formation mechanism investigated by MB2 method using Sys311D basis set. The TS is confined using IRC calculations and the all necessary quantum mechanical calculations performed using Gaussian and software. Result and discussion. The NDMA formation from ADMH during ozonation is take place through 3 steps. The first step is acetaldehyde formation from UDMH during ozonation, and in the second step, they generate acetaldehyde which react with another molecule of UDMH and to give ADMH, acetaldehyde dimethyl hydrazine. And in the final step, the ADMH which undergo ozonation and to form NDMA. And this is the reaction pathway for the acetaldehyde formation from UDMH during ozonation. And the reaction is proceeded by a radical mechanism. In the initial step, hydrogen abstraction is take place from the NH2 moiety of the UDMH by the ozone. And that is the rate determining step also.
Jindamol. Hello.
I think
Jindamol.
there's a problem with the system.
Okay, you are not
Can
audible right now.
anyone join them? I think the system is hacked.
Sirix sir, are you there?
So can
Yes,
I
yes.
relax again?
Sometimes it is not audible.
Yeah, it is not audible. Please relog in if not possible.
Yeah.
Is there any technical issue, Sachin sir?
So the system is not.
No, there is no issue here. Actually, I think it is an issue with the system from where it is presenting. Uh, Jindumul, you can log out from the Zoom and once again log in and continue from where you stop.
Hello.
Sir,
I think we can call the next person and we will give a chance to Jinjumol later.
okay.
Then I invite sorry, Rehin Sule for the presentation.
Good afternoon, sir.
Okay, good afternoon. You please start.
Can you see my slides?
Okay.
Good afternoon, everyone. I am Rahim Sule, working as a research scholar at the Department of Chemistry, CMS College, Kottayam, under the guidance of Dr. B.P. Naik Thomas. Today, I am here to discuss the topic, unveiling the reaction mechanism of N-nitrosodimethyl amine formation from tetramethyl tetraazine during ozonation, a computational study. As we all know that hydrazine is used as a monopropellant for launch trajectory correction as well as the propulsion of small satellites. Not only the hydrazines, but also the substituted hydrazines like monomethyl hydrazines and unsymmetrical dimethyl hydrazines is also used as bipropellants. All these classification of hydrazines are highly carcinogenic and mutagenic substances. On oxidation, these hydrazine, especially 1,1-dimethyl hydrazine, that is unsymmetrical dimethyl hydrazine, undergoes oxidation with ozone, and it could form several transformation products, including tetramethyl tetrazine, acetaldehyde dimethyl hydrazine, formaldehyde dimethyl hydrazole, and highly carcinogenic N-nitrosodimethyl amine. In our study, we have focused on the formation of tetramethyl tetrazine formation from the ozonation of unsymmetrical dimethyl hydrazine, that is UDMH, as well as the formation of NDMA from the ozonation of tetramethyl tetrazine. For that, we have used the computational methodology with molar plus at second order perturbation theory and have used the base set 6311GD. All of the reactants and products involved in the reactions are optimized using this theory and basis set. And the transition state was optimized using T.S.-Barney algorithm. And further, the transition state was confirmed using intrinsic reaction coordinate calculations. We have done all the quantum chemical calculations using Gaussian 9 software program. Okay, then we will look into what we have done in our work. First of all, we have analyzed the reaction mechanism of TMT formation from ozonation of UDMH. This is the proposed mechanism of TMT formation from UDMH. In the initial step, that is, the ozone attracts the unsymmetrical dimethyl hydrazine by abstracting a hydrogen atom from the NH2 moiety, forming a radical intermediate along with the formation of a hydroxyl radical and an oxygen. Then the radical intermediate undergo further reaction with the hydroxyl radical via a transition state TS2, and it forms a highly reactive dimethyl amine nitrate intermediate. The stoichiometric dimerization of D-man intermediate, that is dimethyl amine nitrate intermediate, results in the formation of tetramethyl tetraacene compound. This is the free energy profile obtained for the formation of tetramethyl tetraacene. As we see seen in this free energy profile, the initial step of the hydrogen abstraction from the NH2 moiety of UDMH needs an energy barrier of 15.9 kcal per mole, which act as the rate determining step of the elementary reaction. The calculated activation energy for the formation of dimethyl amine nitrate, very reactive intermediate, needs only an energy barrier of 1.7 kcal per mole, which could be regarded as a barrierless process in the atmosphere. The overall reaction is highly exergonic by 93 kcal per mole and exothermic by 104.7 kcal per mole. This is the calculated thermodynamic properties for the reaction, and from this table we have analyzed that the reactions are both highly exothermic and exergonic. Then we have analyzed the formation of NDMA from, that is N-nitrosodimethylamine from tetramethyl tetraacene. First of all, we have analyzed the reaction mechanism of the formation of NDMA, and in this reaction mechanism, first of all, the ozone molecule attacks the tetramethyl tetraacene via forming an adduct transition state and forms an intermediate having a ring-like structure. In the further step, in the subsequent step, the adduct intermediate undergo cleavage via the second transition state, and it directly forms the NDMA. This is the optimized transition state structure for the formation of adduct TS. Then we have analyzed the free energy profile diagram for the formation of NDMA from the ozonation of TMT, and we have analyzed that the initial formation of the adduct ring-like TS needs an activation barrier of 42.4 kcal per mole, which is a comparatively high energy value. And we have analyzed the reason behind this, and we get the idea that the high activation barrier is attributed by the steric hindrance from the 4-methyl group situated at the 2 terminals of the tetramethyl tetraacene, and the bond dissociation of energy of N double bond N is also very high. That is the reason why this step has this much activation barrier. Moving on to the conclusion from the work, the 2 consecutive hydrogen abstraction from the NH2 moiety in UDMH via the oxidation with ozone leads to a less stable reactive D-man intermediate. The association of 2 molecules of D-man intermediate generates the tetramethyl tetraacene as the major product. The thermochemical analysis of the reaction indicates that all the reaction could take place within the range of, for the formation of tetramethyl tetraacene, all the reaction could take place in the range of 4 to 17 kcal per mole, which could take place in the atmospheric temperature range. And the formation of NDMA, it needs to cross a barrier of 42.4 kcal per mole, which could be credited to the steric effect of 4CH3 placed at the 2 terminals and the high bond dissociation of energy of N double bond N. The estimated rate constant for the reaction is about 8.9 into 10 raised to minus 19 mole per second. Relatively high energy barrier is consistent with the low yield of formation of NDMA during tetramethyl tetraacene ozonation. Thank you.
Any questions? Hello, am I audible?
Yes, sir.
Any questions? Rekin, please show the last slide regarding the conclusion. See, the last one, estimated rate constant
Sir,
for the reaction is
it's about 8.9 into 10 raised to minus 19.
minus 19. What's the unit given?
Mole raised to minus 1, second raised, molecule raised to minus, mole raised to minus 1, second raised to minus 1.
That means it is per mole second.
Yes, sir.
Okay. Or it is mole per second.
No, sir. Mole raised to minus 1, second raised to minus 1.
Okay. Thank you, Rakin, for the nice presentation. And
Thank you, sir.
I think Tindumol maybe given a chance now itself. Tindumol.
Hello, sir.
Are you available?
Yes, sir. I'm trying.
Okay. Are you ready to give your presentation now?
No, sir. The system is not work well. There is some problem with the system.
Okay. Okay, then I will call the next person, Dr. Abu Tahir Afzal. Abu Tahir Afzal.
Yes, good afternoon, sir.
Am
Am I audible? Am I audible?
Yes, sir, you're audible.
Yeah, good afternoon all. My topic is molecular dynamics and the translational rotational coupling of a glass forming pharmaceutical acetohexamide. Basically, this is a glass transition study. So what happens when a liquid is cooled to become a solid? Normally a crystal is formed, but if I cool faster, it will become a glass. So the glass is basically physically, mechanically, it's look like a solid, but it has more degrees of freedom compared to the crystal. So it has rotational degrees of freedom. So we are trying to study the molecular dynamics, which is rotational degrees, rotational motion of the molecules in the glassy state by using broadband dielectric spectroscopy. So the study of glass is very important because we have applications of glass in all fields, because in everyday life we use glass in almost every materials we use. Many materials which are glasses in a glassy state we are using. Like as you can see the applications of glasses, lot of applications is there in the biology also, and in pharmaceutical also. The glassy state is more important because the crystalline drug is less soluble compared to the amorphous drug. So if we prepare the drug in the amorphous phase, it will have more solubility. Accordingly, it will have more bioavailability. But the problem is the amorphous phase in the shell during the shelf life, it may return back to the crystalline phase. So we want to study the stability of the amorphous phase in the shelf life. So for that, we have to characterize the supercooled liquid state and the glassy state in the glass using this molecular dynamics. So we can estimate the stability of the amorphous phase. So the different areas of interest of this glassy state is listed in this slide. And for understanding the glass transition temperature, we use the differential scanning calorimetry. And as we can see, the using the endothermic exothermic curve, we can find the glass transition temperature of the sample. This is a typical DSC curve. And the dielectric study is done by a spectrometer, which is using a AC and a capacitor. So in this case, the sample is kept between the plates of the capacitor, and the AC is applied, and the frequency is from 10⁻² to 10⁻³ 7 hertz, which I am used, and the temperature is used from minus that is 123 Kelvin up to that melting temperature, that is minus 150 degrees Celsius to melting temperature, because that will be in the glassy state. So first of all, we have to melt the sample to become a liquid, and then quench cool the liquid to become a glass. And then after in the glassy state, at different temperatures of the glassy state, we will measure the molecular dynamics, and in the supercooled liquid state also we will measure the molecular dynamics, and from that data we will understand the stability of this seed. So what happens is there is a change in the dielectric relaxation. During a dielectric relaxation, the real part, imaginary part of the dielectric constant changes like this. This is a step-like change which corresponds to the primary relaxation, which is due to the cooperative motion of the molecules, which is dipoles. So the dipole, the molecules are dipoles, and the secondary relaxation corresponds to the change in the dielectric constant due to the local motion of the molecules. Accordingly, there will be a peak in the imaginary part of the dielectric constant, which corresponds to dielectric loss. So from the dielectric peak, loss peak, we can understand the frequency or the time constant of the relaxation. So the primary and secondary relaxation will give a lot of information about the mobility of the molecule in the glassy state, from which we can understand and estimate the stability of the amorphous phase in the glassy state. So this is the rationale of the study, and the drug is the drug is acting on the action site, but the problem is the solubility is a problem. As many of the drug is not absorbed in the body fluid. So we conducted this study for understanding maybe some life-saving drugs which are not available in the market due to the problem of the low bioavailability or low solubility. These drugs can be studied using this amorphous phase, can be converted in amorphous phase, and then we studying the amorphous stability, we can introduce these drugs into the market because of these are the life-saving drugs. So the material which I took is acetohexamide, is a drug, anti-diabetic drug, that melting temperature, water solubility, all these things are noted. And DAC is used to understand the glass transition temperature, and the dielectric spectroscopy is used to understand the molecular mobility. This is the principle of the measurement. And here you can see the frequency range, where you can see the in this frequency 10 raised to -2 to 10 raised to 9 hertz, the dipolar relaxation, that is orientational polarization, is the reason that causes a change in the dielectric constant or the dielectric spectrum. So if I have a data for different temperatures, we'll get a BDS spectrum, that is broadband dielectric spectrum. So the different temperatures, these curves at the different temperatures will give you some parameters which are crucial to understand, estimate the stability of the amorphous phase. The apparatus used is shown in this figure. This is the DAC curve of the acetohexamide. The glass transition temperature is shown in this table. And yeah, you can see here, this is the BDS curve of the acetohexamide during cooling. The dielectric constant and the temperature is plotted. And for the 4 frequencies, you can see here at low temperatures, there is a curve B corresponding to the secondary relaxation. At the same experiment, at the high temperatures, you are getting some high values of dielectric constant, which corresponds to DC conductivity. But actually, there is a primary process, which is due to the high conductivity, this process is not observed, it is masked. But if I am using the modulus representation, which is the reciprocal of dielectric constant, I am getting the peaks that is corresponding to the conductivity relaxation or the dipolar relaxation. So similarly, we can plot the frequency spectrum. What you are seeing now is the temperature spectrum, that is x-axis is temperature. But here you can see the frequency in the x-axis, the dielectric constant in the dielectric loss, which is imaginary part in the y-axis. And you can see here, in the glassy state, I am getting peaks, which is corresponding to the secondary relaxation. And this is also the dielectric loss. at above high temperature, that is still in the glassy state. See, when I plotted these things in the modulus, I am also getting similar graphs at the glassy state, because it is at the low temperature. And this is also in the glassy state, that is 313 Kelvin is below the glass transition temperature. So at the glassy state, I'm getting relaxation, which is secondary relaxation, both in the modulus representation and as well as in the dielectric representation. So after that, what we do is we will plot a Arrhenius graph, that is nothing but the log tau. That is, we find the, as I told you, from the peak of this, we get the frequency and then we get the time. That is the time of the relaxation, and then we convert it into log tau. So that is plotted in the y-axis. And then the corresponding temperature is taken in the reciprocal, 1000 by T is plotted in the x-axis. So what is the use of this is we will understand the temperature evolution of the relaxation process. That is, I told you, there are two types of relaxation. One is a primary relaxation above the glass transition temperature. That is, this is the primary relaxation, that is alpha relaxation. This is the secondary relaxation, because since I am plotting in the reciprocal of temperature, the higher values corresponds to the low temperatures. So that this right side of this dot represents the glassy state. So in the glassy state, you can see the data, the points are from the permittivity representation and from the modulus representation. That means I have determined the time or calculated the time from the spectra or from the modulus spectra as well as in the permittivity spectra. And then I plotted in this Arrhenius diagram. I found that these are matching, these are corresponding, and that means both the representation represents the relaxation from the same origin. So that means this is a process called as translation rotational coupling, because the modulus representation is basically from the conductivity relaxation. That is, conductivity relaxation is the translation of ions, and the dielectric spectrum is only due to the dipolar relaxation or the orientational polarization of the dipoles. So if I am getting the same time and the same temperature, which means they are superimposing in the glassy state, that means in the glassy state, there is a coupling between the translation motion and rotation motion. Moreover, you can see in the supercooled liquid state, that is above the glassy state, the alpha relaxation is shown non-Arrhenius, that means non-linear temperature dependence, which is corresponding to the non-Debye process. That is a normal Debye relaxation, non-Debye relaxation. And finally, we fitted this with the VFT equation, which is normally used for fitting the Arrhenius of the alpha relaxation. And we got the parameters. These parameters are very crucial for understanding the stability of the glassy state. From this, we can understand that there are two relaxations in the glassy state, and the fragility corresponds to the strength of the glassy state. That is, how much it is glassy state is whether fragile or strong. So the value of 51 corresponds to intermediate fragile, and the glass transition temperature is 320 Kelvin. That is above the room temperature. That means correspondingly, which means more the value of glass transition temperature, more stability it is. That means more stable it has. So this is what the most important values of conclusion. There are many things to show. Because of the time limit, I am showing this. And one more thing is by the DFT method, we can, using the Gaussian software, we have conducted a theoretical study and plotted this graph. That is, we rotated a particular side chain of the molecule, and then we draw the energy scan diagram, and this energy, which is corresponding to the energy of the secondary relaxation, activation energy of the secondary relaxation, that is found from this Arrhenius diagram. So this is something a correspondence. That means using we are verifying the origin of the secondary relaxation by theoretical computation method, and this helps us. And there is no other method to understand the origin of the secondary relaxation, and this is the only method which we can understand from the particular side chain or particular part of the molecule which is responsible for the origin of the secondary relaxation. So that is what we have conducted. So by this, we come to the end of this presentation. Thank you.
Hello, any questions from the audience? Any questions? So, Abu Tahir, whether the DFT calculations, DFT results of the DFT calculations are matching with the experimental results?
Yes, yes. Yes.
Have you compared it in your slides?
Sir, this is what 36 kilojoule. And in this graph, 33.62 kilojoules. There are two secondary relaxations.
It's almost,
so one of the relaxation is approximately matching, but by different methods we can try and to get more proper results.
Then I need a clarification from slide to 57. Slide 57.
57. 57.
57. Okay. What is the variation? What is the effect of this frequency?
This is, but the frequency is fixed and it is cooled. The sample is cooled.
Is there any systematic variation? No.
This corresponds to a relaxation process. That is why a peak is, we are getting a peak. But in the secondary, the lower temperature, we are getting two peaks, which corresponds to two secondary relaxations. It is just to just to understand the presence of relaxation when we cool this, because we have to convert this solid to glass. So we cool it to melt it to become a liquid, and then we cool it to become a solid. And during this process, we just measure the dielectric constant at different frequencies, at 4 fixed test frequencies, and the data shows a peak, because what we can say is, as the frequency increases, the temperature increases. See, the blue is 100 kilohertz. So the blue peak is at higher temperature, which means as temperature increases, the frequency is increasing.
When the frequency increases, what will happen?
Yeah, the frequency, when the temperature increases, the molecules rotate faster because of the thermal energy. That is a thermal activated process. So when the temperature increases, the rotational speed will increase, or a frequency will increase.
Then 1 kilohertz and 100 hertz gives almost the same results, I think.
1 kilohertz and 100. No, 1 kilohertz is black color.
Yes.
And 100 hertz is green color.
Green.
There is a shift in the temperature.
Okay. Thank you.
Thanks.
Abu Tahir.
Thanks. Thank you.
Now I invite Monica F for the presentation.
Yes, sir. Good evening, sir. Good evening. Can I audible?
Yeah.
Yes. 1 minute, sir. 1 minute. Good evening, sir. I am Monica, working as assistant professor in St. Joseph College for Women, Alappuzha. Sir, screen shareable, sir? Okay. So, in my title is radon exhalation rates in soil sample along the coastal region of Nendagara, Kollam district. Abstract, indoor radon has been recognized as one of the health hazards for the people. The radon exhaled from the soil accumulate in indoor environment and contribute to 55% of inhalation dose. In the present work, I have find out the exhalation rate of radon from the soil sample collected from the coastal region of Nendagara, Kollam district using canister technique. There are two types of radiation, ionizing and non-ionizing. Ionizing radiation means highly penetrating radiation such as gamma or heavy particles such as beta and alpha particle, and non-ionizing radiation mean low energy electromagnetic waves. The important sources of ionizing radiation include natural background radiation and man-made radiation. Cosmic radiation means the radiation enters into human body due to the from outside, from sun rays. Terrestrial radiation means the radiation enters into human body due to the presence of radioactive nuclides which are already present on the crust, that is from soil sample, water, and from vegetation. Radon properties. Radon is a colorless, odorless, tasteless radioactive gas which is formed from the radioactive decay of uranium. And the radon has an half-life of 3.8 days. Important health effects of radon. Humans may receive exposure to radon through water or air that is injected. Because radon is vapor, it can easily be inhaled. Experimental setup. In order to find out the exhalation rate of radon, here I have used a method called canister technique. Here, the soil sample is taken in a standard can and it is sealed. At the end of the at the upper end of the lid, I have placed an LR115 detector. The experimental setup is kept for about 100 days. And after 100 days, we have removed that that LR115 film H, and the system can be counted by using spark counter. From the spark counter, we can get the track density, and from the track density, I have able to find out the exhalation rate of radon from the soil samples. Mass and surface. Table 1 gives about the effective radium content, mass, and surface exhalation rate for the soil sample along the coastal region of Nendagara is shown below. Location, sample code, effective radium concentration, surface exhalation rate, and mass exhalation rate. The value of effective radium content vary from 0.22 to 0.72 becquerel per kilogram, and these values are lower than the recommended unscare value, that is 370 becquerel per kilogram. The mass exhalation rate varies from 33.11 milligram per hour. Exhalation rate from the soil sample and the world average value, that is 56 millibecquerel per meter square per hour. Conclusion, the radium concentration was found safe limit within the unscare recommended value. The result reveals that the area is safe as far as the health hazards of radium and radon exhalation rate. The study area is advisable to be used as residential area. These results are reported for the first time with the best of my knowledge. Thank you. Thank you.
Thank you, Dr. Monica.
Okay, sir.
Any questions from the participants? If not, we can move on to the next presentation by Priyadarshini D. Priyadarshini D.
Good afternoon to you all. Hello?
Good afternoon.
Am I audible?
You are audible, but okay. You can start now.
Thank you, sir. Good afternoon to you all. I am Priyadarshini, St. Jude's College, Tuttur. Now I am going to present topic is growth and characterization of pure and sulfuric acid doped urea single crystals. Abstract. Advancement in crystal growth has led to the discovery of new materials with enhanced properties. Solvent evaporation technique was used to crystallize urea at a constant temperature. In the present investigation, pure urea was synthesized. The effect of sulfuric acid in the crystallization of urea was investigated. The ground crystals were characterized for their structure, elemental, micromorphological, and microharness features. Introduction. Technology is based on single crystals of nonlinear optical, ferroelectric semiconductor, superconductor, and acousto-optic materials. Crystallization from aqueous solution by solvent evaporation is an important simple technique. Crystals obtained by this technique possess good qualities for applications. Urea is used as fertilizers, treat dry and rough skin conditions. Industrial applications in photonics, optical computing, optical communication, and optical information processing. Experimental materials and methods: AR grade urea, sulfuric acid, triple distilled water, magnetic stirrer. Synthesis: urea was synthesized using analog grade urea and sulfuric acid in the ratio 2:1. Crystallization: mother solution prepared 75 ml of saturated solution of urea. Experimental solution used 50 ml and 25 ml in 2 beakers. The pH of urea solution 7. It is used to measure pH meter. Dopant sulfuric acid used few drops. The pH of sulfuric acid doped urea 7.4. Technique used solvent evaporation technique. Temperature maintained 29 degrees Celsius. Harvesting time pure in 3 days and doped in 26 days. Results and discussion. The investigation shows that the sulfuric acid doped urea crystals change in shape. XRD. The pattern of urea and doped urea shows their peaks in figure. The lattice parameter of the ground urea was in good agreement with the JCPDS value. The lattice parameter of the sulfuric acid was found to be A and C value is increased. Fourier transform infrared analysis. The FTIR spectrum shows urea and sulfuric acid doped urea crystals. FTIR spectral assignment of urea and sulfuric acid doped urea shows that urea peaks and sulfuric acid doped urea peaks. Some urea peaks are absent in the doped urea like 3738 CH stretch, 3475.52 OH stretch, 3205.47 NH stretch, 3031.89 CH stretch, 2931.60 CH stretch, etc. These peaks are absent in doped urea. So the spectral assignment of the pure urea incorporate with the sulfuric acid doped urea. Elemental analysis. This EDAX spectrum shows peaks of carbon, nitrogen, oxygen, and sulfur present. Carbon, nitrogen, oxygen elements are present in the urea, and carbon, nitrogen, oxygen, and sulfur are present in the doped urea. Carbon, nitrogen, oxygen are present in the urea and doped urea, but sulfur is only present in the doped urea. EDAX data. On comparing the elemental data of urea and sulfuric acid doped urea, 0.01 atomic weight percentage and 0.02 weight percentage of sulfur was found in sulfuric acid doped urea. The sulfur element is present in the doped urea crystal shows that sulfur was substituted in sulfuric acid doped urea was also found to be reduced. The atomic weight percentage and weight percentage of the element of oxygen, carbon, nitrogen present in sulfuric acid doped urea was found to be decreased. This may be attributed to the incorporation of sulfuric acid in the urea. Surface analysis. On visualizing the sum of urea, the surface was found to be not smooth. In the sulfuric acid doped urea, the surface was not smooth, but the presence of clusters of microcrystallities have both regular and irregular patterns were visualized. This may be due to the effect of doped sulfuric acid. microhardness. The viscous microhardness of the ground pure and sulfuric acid doped urea crystal is determined using Leitz-Witzler hardness tester fitted with a viscous diamond pyramidal indenter. The indentations are made on the polished crystal for the loads of 25, 50, and 100 grams. The viscous microhardness number, hardness values HB equal to 1.85444 P divided by D kilogram per millimeter square. The values are given in the table. According to the Mayer's law, the plot of log P versus log D is shown in figure. Using the plot, the value of the work hardening coefficient of N is estimated. According to Honeyman, the value of N is less than 2 for hard material and more than 2 for soft material. Hence, it is concluded that the urea value is N equal to 0.8683 is a hard material and sulfuric acid doped urea value N equal to 1.2712 is a hard material. Conclusion, single crystals of pure and sulfuric acid doped urea have been grown by slow evaporation technique. Investigation shows that the sulfuric acid doped urea crystals change in shape. X-ray diffraction studies confirmed that sulfuric acid doped urea crystallized in tetragonal system with a space group P4/21 meter. FTIR spectral analysis confirmed the presence of functional groups in the crystals. EDAX shows the various constituent atoms present in the urea and doped urea. Some picture shows different surface features of urea and doped. Microhardness study was used to found the material hard of urea and doped. Reference. Thank you.
Thank you, Priyadarshini. But I have a couple of questions.
Okay, sir.
So you please display the last slide of conclusion.
Okay, sir.
So what is the third one?
X-ray diffraction studies, sir. X-ray diffraction studies confirm that sulfuric acid doped urea crystallized in tetragonal system with a space group P4/21 meter.
P4 to
1.
1.
Yes, sir.
Please repeat.
P4/21 meter.
See, it's not clear to me. Please repeat.
P4/21 meter.
Meter.
Yes, sir.
Meter.
Yes, sir.
Then fifth one.
EDAX shows the various constituent atoms present in the urea and doped urea.
EDAX. You have given it as EDXA.
Yes, sir.
Is it the
Elemental differential X-ray analysis.
It is EDXA or EDAX?
It's probably, sorry, sir, EDXA.
Then the slide of surface analysis. You please show it.
Okay, sir.
Next one. This one, surface analysis. Okay.
Yes, sir.
What's the spelling of that surface?
SURFACE, sir.
You given it as?
SURFACE.
Is it FSCE or FSCC? In your slide it is? See, it's
Yes.
not. It is not clearly visible to me. Okay, leave it. Okay, leave it. Then what was the pH of this mother urea solution?
Urea solution 7, sir. 7.
It is 7.
Yes, sir.
Okay. It is measured by pH meter.
Yes, sir.
Then you added sulfuric acid as dopant, a few drops of sulfuric acid.
Yes, sir.
Then how the pH of the sulfuric acid doped urea becomes 7.4?
That due to the dopant compounds, sir.
Dopant?
Is dopant.
What is the pH range of sulfuric acid or any acid?
Sulfuric acid range is 6 or 5, sir.
6.5.
6 or 5.
6 or 5.
Yes, sir.
So it is an acid. Sulfuric acid is a strong acid.
Yes, sir.
Then what is the range of acidic pH value of acidic region and base region?
Sir?
What is the pH range of acidic materials and basic materials?
1 to 7 is acidic materials.
1 to 7 is acidic and
7 to
okay. Above 7 is basic materials.
Base materials.
Then pH of your urea solution was a 7. And when you added some sulfuric acid to it, how the pH value increases or shifts to the basic range? How it comes 7.4?
So, sir, it's my mistake, sir. It's my mistake, sir. I incorrected, sir. I will correct it, sir.
Okay, you should correct it.
I put the wrong value, sir.
Because
sir,
these things are a very, very basic but very important.
Sorry.
And again, regarding your micro hardness analysis,
okay, sir.
You confirmed or you made a conclusion that when sulfuric acid is doped in urea, it becomes more strong, more hard materials. But all these conclusions were reached only using 3 weights, 25 gram, 50 gram, and 100 grams. And your graph is not at all saturating. It is increasing. I think a better conclusion is obtained after repeating it with some more weights. So that is the value of log P gets saturated.
Yes.
Okay. Okay, don't make mistakes in the slides.
Okay, sir.
And again, confirm what is the space group, whether it is P4 bar 21 M or meter. Just 1 M, not meter. Okay.
Okay, sir.
Okay. Okay. Thank you, Priyadarshini. Now I invite Naina Devaraj for the presentation.
Hello, sir.
Naina Devaraj.
Sir, am I audible? Hello. Hello, sir. Hello.
Naina Devaraj, are you present?
Yeah. Hello.
Okay. Okay. Now you can start.
Am I audible, sir?
You are audible, but voice is low, I think.
Hello. Is it better now? Okay. Okay, let me start. I think screen is also visible.
Yeah.
Good afternoon, everyone. My name is Naina Devraj. I'm a research scholar in the Department of Physics, National Institute of Technology, Karnataka. Here I am presenting on the topic spin-dependent Schottky barriers in CRI3WSC2 magnetic van der Waals heterojunction and its application in the construction of spintronic devices. Data storage is an integral part of computing ecosystem. The initial storage devices are called punch cards with a storage capacity of only 100 bytes. Later, hard disks were introduced as fixed storage devices. The initial one weighed only 5 MB of data. Recent data in a hard disk, which is lighter than a notebook. Later, portable storage devices like floppy disk and compact disk were introduced. And now we have flashcards for...
Is it audible to everyone?
No, sir, I don't think it's audible now.
Is it audible?
Hello? Okay, actually what is happening is my the sound after should I continue or should I try later?
Hello, Naina?
Hello? Hello, sir?
Yes. Continue.
Automatically reducing it. This microphone sound is automatically reducing. Hello? Should I continue? I think there's an issue with my system. Or should I try later? Yeah, that is automatically reducing.
Speaker.
Reducing by manual. Yeah, speaker.
Top one. Reduce it.
After some time, it is coming back. See, it's coming back automatically. I think that is the issue. Hello? Okay.
Oh, it's gone again.
Yeah, it's going again. I don't know what's the issue, but it is going back again and again. Should I stop? If it is not audible, that's no point. Hello? Hello? Can I proceed? Hello, sir. What should I do? Hello? Okay. Okay, now is it fine?
Okay. Now it's okay.
Hello? Sir, can I try later? Try with my phone once. Whether it is working with my phone.
Okay. I will give you the chance.
Okay, sir. Okay.
Now it is the turn of Adira Rajan.
Yes, sir. Am I audible, sir?
Okay.
Sir, am I audible?
Yes, Adira. Yes.
Okay, sir. Is the slide, sir, visible, sir?
Okay.
Okay, sir. Good afternoon, everyone. Myself, Adira Rajan from Department of Physics, University of Kerala, working under the guidance of Dr. Subodhji and Dr. CBKS. Today, I'm going to present my work entitled Multi-Layered Conducting Magnetic Composites for Enhanced Electromagnetic Interference Shielding, a Simulation-Oriented Study. As we know that with the dawn of newer technologies such as the fifth generation network and Internet of Things, our life has become so much easier. However, this comes with a price. The large amount of electromagnetic radiation that we use leave us vulnerable to a large amount of electromagnetic pollution as well. This pollution, commonly known as electromagnetic interference, is any external effect that disturb electrical circuits or biological systems by way of induction or radiation. And this is not only harmful to our sophisticated devices
processes, but also to the biological systems as well. Fortunately, this electromagnetic radiations can be shielded by using materials known as EMI shielding materials by employing different mechanisms such as reflection, absorption, and multiple internal reflections. So in this study, we are introducing a novel concept of simulation of materials for EMI shielding applications, which is a rarely exploited and excellent strategy to predict the EMI shielding effectiveness of a particular material from its electromagnetic parameters only. As you can see here, when we go for material fabrication, it is a very time-consuming as well as a non-economical process to fabricate a lot of materials and selecting one of the best among them. So you can introduce shield simulation in this, and after optimizing the electromagnetic parameters a number of times, you can go to the fabrication process. Thereby you can reduce a lot of time, cost, and effort. Okay, and so we are going for layered structuring of magnetic and conducting composites, which is also an interesting strategy that can be adopted to enhance the AMI shielding performance of materials. This work is a pioneer investigation on implementing the simulation-based approach to engineer EMI shielding structures with enhanced performance. And also, this is in the study, we want to highlight two factors. First one is how simulation is an important, what is the importance of simulation in this particular field, and second one is how the macrostructural arrangement or engineering of material is beneficial in providing a higher or better EMI shielding performance. This work is divided into two parts. First one is simulation of shielding structures, and it is carried out using ANSYS HFSS software, which is high frequency structure simulator software in the K-band region, and from 1826.5 gigahertz. And in order to simulate particular structures, we need to give some input parameters, and these input parameters are the electromagnetic parameters and electrical conductivity of the materials listed here. And for this, all our materials are polymer based materials, and our polymer is PVDF, and our conducting pillar is carbon black, and magnetic pillar is a hexagonal ferrite known as barium hexaferrite, and the CBBF for PVDF composite denoted as carbon black, BF for materials in PVDF, that is simple conducting magnetic composites, and CMC and MCM refers to as conducting magnetic conducting and magnetic conducting magnetic composites, where a magnetic material is sandwiched in between two conducting layers and a conducting material is sandwiched in two magnetic layers respectively. From the shielding studies of the simulated materials, it is clear that the CMC layered structure exhibited maximum shielding effectiveness other than out of the many fabricated materials, that is the PVDF, conducting black PVDF composite, barium hexaferrite PVDF composite, conducting magnetic carbon black BF for simple composite, and the layered structures. And this can be attributed towards the importance of engineering in materials rather than going for a novel material. If you are giving importance towards the engineering of the particular material, it will give a better EMI shielding performance. And also we have simulated various layered structures within the same thickness, and then as the number of layers are increased from 3 to 15, let's see what happens. And from this, it is clear that as the number of layers increasing in the CMC structures, there is no particular variation in the total shielding effectiveness. It is already in the range of 50, between 55 and 60. And in the MCM structures, it is very interesting to note that as the number of layers increase from 3 to 15, the total shielding effectiveness is increased. Total shielding effectiveness is increased from around 30 to 50 dB. There is no reflection based shielding increases, only the absorption based shielding is increased, and this can be attributed to the impedance matching of the magnetic material that we have given in the first place. And also, in order to test our theory, we have fabricated all the shielding structures using coagulation and hot pressing method, and casting and hot pressing method. And this is the field division scanning electron microscopy, and from this we can see that there is no diffusion between the magnetic and conducting layer in any of the composites, and that is the CMC and MCM composite. So it is clear that there is no diffusion, and the layers are intact even after hot pressing. And from the electrical conductivity study, it is clear that even though the CMC composite exhibited a lower conductivity than the conducting magnetic PVDF and carbon black PVDF composite, the CMC composite exhibited superior shielding behavior as expected from the simulation studies. Also, the simulated and measured values are in agreement with each other, as we can see that it is 57.08% dB here, and it is 57.52 for the measured values. And the agreement between the EMR shielding values of the simulated structures and the synthesized compounds reveal that simulation is an interesting tool to predict the EMR shielding properties of systems. Concluding, we want to highlight two factors that is, if we want to fabricate a particular material for EMI shielding application, rather than going for a material, always it is very good to go for a novel material. It is always important to design and engineer the material for its better application potential. And also, rather than in this post-pandemic era, and also the pandemic is going on, and we can say that if you want to go for a cost-effective technique, so this strategy such as a simulation can come in handy, and you can go for simulation. You can optimize the electromagnetic properties and give a better shielding material with a better shielding effectiveness. And we would like to acknowledge Kerala State Council for Science, Technology and Environment through the research grant, and University of Kerala for providing the research facilities. Thank you.
Thank you, Aditya.
Yes, sir.
So, you are confident about the accuracy of your simulation?
Yes, sir. Yes, I'm confident, sir, because we have carried out the, in order to test that our theory works or not, we first started with PVDF. That is, PVDF is a simple composite. There is no fillers in it. And we have tested it in our lab from 18 to 26 gigahertz frequency in the K-band region using a waveguide method measurement. And it is found that it is actually very much matching, and is in the simulation method it is 1.93, and when it comes to the measurement it is 1.66 only, and this is a well matching method. And that after we have measured all simple materials, that we went to test the other materials also, that is the layered materials and the conducting magnetic composite.
Okay, now what about the control of thickness while you prepare your samples?
Yes, sir. Yes, sir. Yeah, yes. Here, sir. Sir, we were looking into that. What happening in layered composites is that first the electromagnetic material enters into the material. If we provide layering, it will the material will are continuously reflected back, and further it will be get absorbed by the material itself. So inside the material itself, so there will be no electromagnetic radiation coming out from here. And also it is very important to note that we don't need primary reflections. That is, if the electromagnetic radiation reflected from here, then it will go back to the nature only. We need a material having higher absorption potential. So we were wondering that what will happen if the number of layers are increasing. We are giving more interfaces to reflect and thereby absorption of the electromagnetic radiation. So that's why we have incorporated in a definite thickness only. All these material have a thickness of 1.5 mm. However, we have reduced only the thickness of the individual layers. Here, the thickness of the individual layer is 1.5 mm. So there are 3 layers, 0.5 mm thickness is there. And when you have increased the number of layers to 5, the thickness will be reduced to 0.1. And this happens in all the materials. And that the last one, that is the 15 layers that we can actually fabricate. It is quite hard to fabricate. We don't know about the fabrication of this particular one. We have fabricated till here, and it was matching well. And this one, it is it is a little bit hard because the layers are very, very thin. But the number of layers increase. If you increase the number of layers, there is definitely increase in the total shielding effectiveness for the MCM composites, because first of all, if we are using a magnetic material here, it will facilitate impedance matching. That is, the impedance of the free space will match with the material, and electromagnetic radiation will go in directly rather than for a conducting material. And this will get reflected a number of times inside the material, and eventually it will get absorbed by the material, and there will be a very, very low radiation will coming out. Like 99.9% radiation will get absorbed. As we can see from the measured value, it is around 60 and 40.
Is there any optimum value of the thickness?
Sir, for EMI shielding FTS applications, actually we can go up to 2 millimeter. I think it is good to reduce it to 2 millimeter only. I mean, if you go, there are reports that suggest that you can go beyond 2 millimeter radius, but it is actually it is not commercially feasible. So if it is 2 millimeter, you can if it is less than 2 millimeter, that's good for economically. If you want to give your material for industrial applications, it will be restrict the thickness as much as less. It's good to reduce it to 2 millimeter, less than 2 millimeter.
Okay. Thank you, Aditya, for the nice presentation.
Thank you, sir. Thank you.
Then I invite Manija, Dr. Manija M. Manija.
Yes, sir.
Okay. You can start now.
Can you see my slides, sir?
Yes.
Now, good afternoon to all. Now, the topic is temperature stimulated band gap tailoring in smart chromogenic WO3.33H2. Hydrated form of WO3 is chromogenic in nature. And why it is called smart material? Because when we apply some stimulus such as temperature, pressure, or voltage, etc., then it changes its color, and even just when remove the stimulus, it will regain its original color. Hence, it is called smart material. Now, we are interested in hydrated form of WO3.33H2O. The motivation behind this work is the different applications of thermochromic material in different fields, such as smart window, medical thermography, cosmetics, thermometers, etc. And now, first of all, we prepared the sample via hydrothermal technique. The sample is prepared via hydrothermal technique from sodium tungstate precursors using a series of reaction techniques, and the obtained sample is confirmed from X-ray diffraction technique. The X-ray diffraction profiles of the sample, you can see in the figure that the sample is phase pure and the orthorhombic phase of the sample is confirmed. The growth direction of the sample is also along the C-axis, that's along C002 plane. This is the ritual refined structure of this material at room temperature. The polyhedral structure gives two types of WO6 octahedra.
Manija?
Oh, sir.
Slides are not moving, I think. Or is it my own?
Okay, sir. Now, can you see second slide, sir? Thermochromic materials in different.
I have seen.
Then synthesis technique.
Okay.
Then fourth one, ritual refined structure. Is it clear, sir?
Okay.
Then this is the ritual refined structure of this material at room temperature. And the polyhedrals, this is the polyhedral structure of the sample. And the polyhedral structure consists of two types of WO6 octahedra. The two types of in WO6 octahedra, tungsten atom is at the center, which is surrounded by 6 oxygen atoms. And between these two WO6 octahedra, there is water molecule is present. There are two types of water molecules in orthorhombic WO3.33H2O. One type of water molecule is coordinately bonded to these two types of oxygen atoms, or it is called intercalated water molecules. Thus, the water molecule connected along the C-axis between these two types of WO6 octahedra gives the layered nature to this material. This layered nature is very important when we characterize the material in different fields. Another important property of the water molecule present in the material is the Groth's mechanism. The Groth's mechanism is that when the water molecule consists, in water molecule, there are 2 hydrogen and oxygen atoms. When we give the temperature stimulus, one of the H plus ions get liberated and it will move towards the another water molecules. And for a small fraction of second, hydronium ions is formed. Then this knock out another hydrogen ion for conduction, and thus the proton hopping occurs to this material, gives the Groth's mechanism to the material. Thus, the sample is annealed to different temperatures, and the TGA measurements shows that when the sample is annealed up to 300 degrees Celsius, the material remains in its hydrated form due to its intercalated water content. Now, we are interested in the chromogenic properties of this material. The thermochromism means simply the color change in the material when the temperature stimulus is given. To study the thermochromic property of the material, all throughout the study, we kept the sample on a hot plate and giving the temperature. At different temperatures, we take the reflection of, for the different temperatures, we take the reflectance of the sample with respect to wavelength, and at different temperatures, we take the photograph of the sample and it is also shown in the inset. Clearly from the inset, we can identify the color change of this material from 30 to 190 degrees Celsius. Also, there is change in band gap associated with this color change. This band gap is calculated from the top plot obtained from the sample. This is the top plot is also shown here in the inset, and from the top plot we can obtain the band gap of this material. Band gap also changes with temperature and it varies from 2.8 to 3.15 electron volt with respect to temperature. To identify the reason for the change in band gap and also to identify the reason for the thermochromism, we consider the absorption spectra of the sample. From the absorption spectra, we get the IVCT band at all temperatures and which corresponds to the intervalence charge transfer taking place in the compound. In the early stages of the study, we identified that the material has multivalency and it shows W6 plus and W5 plus, which is confirmed from IDAX and XPS measurements. And this shows the swapping of oxidation state between these two states with the absorption of energy. The reductant oxidant pair W6 plus and W5 plus taking place in homovalent IVCT mechanism causes metal to metal charge transfer and which is referred to as precursor complexes. Due to direct D to D transition, electron hop between these cations and the coloration occur in this material. These are the conclusions obtained in the study and some of the references, and thank you.
Thank you, Manija. How will you identify the 5 plus and the 6 plus state from the EDAX?
Sir, in the early stages of measurements, we identified that the XPS is not included. May I take the XPS of the sample?
No, the IDAX.
Okay, sir. Thanks. Is the slide is clear, sir?
Yes.
From this IDAX and XPS measurement, we identified the presence of W6 plus, and also we deconvoluted the XPS spectra of the sample, and from the calculation of the
I agree, Manija, but from IDAX, how will you identify it? That's my question.
From IDAX, okay. From the IDAX, we get different weight and atomic percentage and concentration of the sample, tungsten and oxygen. Different weight percentage and atomic percentage is available from IDAX spectra. Then by calculating the ratio, we can identify that the presence of non-stoichiometry is present in IDAX, and the presence of non-stoichiometry identify W6 plus state in the material.
See, how will you get that ratio? W/O equal to 1:2.77.
Okay, sir. From the EDAX spectra, we get weight percentage, atomic percentage, and concentration percentage of this material. Then there is a calculation regarding the weight percentage and the atomic percentage and concentration. Then using the calculation, we can find W/O equal to 1:2.77. That is just theoretical calculation using this experimental data.
Then how will you differentiate the presence of W6 plus and W5 plus from the DAX?
So they have already given that there are tungsten and oxygen atom present in the compound, and this oxygen and tungsten atom concentration gives that there is presence of non-stoichiometry in the compound, and the presence of non-stoichiometry then we took XP to identify the non-stoichiometry. We use XPS, DAX result. Then XPS is taken to identify the presence of W5 plus and W6 plus separate.
Okay, thank you, Manija.
Thanks.
Then let me call Dr. K.F. Kiran. Dr. Kiran. Dr. Kiran. If Dr. Kiran is absent, now it's the turn of Aparna PM.
Yes, sir.
You can start now.
So my slides are visible, right?
Yes.
Okay. Good evening, all. I am Abarna, working under Dr. K.P. Surendran at CSIR NIST, Trivandrum. The presentation is entitled as Hydrothermal Synthesis of Polymer Composite Aerogels for Effective Electromagnetic Interference Shielding. Electromagnetic interference, or EMI, is any kind of disturbance caused by electromagnetic waves that affects the performance of systems or devices. And an EMI shield is used to protect our system or a region from these unwanted radiations. And an EMI shield works through mainly three mechanisms: absorption, reflection, and multiple reflections. And the performance of an EMI shield is measured in terms of shielding effectiveness in the units of decibels. And the features of an efficient EMI shield are: shielding efficiency should be greater than 20 dB. At 20 dB shielding efficiency means the shield is blocking 99% of radiations incident on it. And corrosion resistance, absorption dominant shielding mechanism, because if it is a reflection, the reflected waves are again polluting the environment. And appropriate mechanical strength should be there. Conventionally, metallic materials were used for this shielding purpose, but due to its heaviness and corrosive nature, they were replaced by carbon-based materials, mixing composite 2D materials, and conducting polymer composites and porous composites. Now, here we prepared a B2O5 Pani aerogel, which is a porous composite, and through a simple hydrothermal route. We started with ammonium metavanadate and we made a V2O5 nanowire dispersion. It was subjected to heat treatment, hydrothermal treatment for 24 hours at 140 degrees Celsius, and we got V2O5 hydrogel. And this hydrogel was immersed in aniline dispersion to get V2O5 Pani hydrogel. It was freeze-dried to obtain V2O5 Pani aerogel. You can see the photographic image of V2O5 Pani aerogel. Here. The pure V2O5 hydrogel was directly freeze-dried to get V2O5 pure V2O5 hydrogel, which was freeze-dried to get V2O5 aerogel, just for comparison studies. It was coded as VHT, and the composite material was coded as VPHTH. And Then 10 image shows the ultra long nanowire morphology of VHD. In the composite sample, you can see the polymer wraps these nanowires, and so these nanowires become conducting due to the presence of conducting polymer polyamide. And the SEM image shows highly porous and layered structure, which is highly beneficial for absorption dominant shielding, because the vast surface area provided by this porous and layered structure helps multiple internal reflections and scattering, due to which these EM waves are get dissipated. Spectroscopic analysis like Raman, FTIR, and XPS confirms the presence of polymerization, and BET isotherm was studied to study the porosity and surface area, and it was seen that the surface area of composite sample was improved by 3 times compared to the pristine sample. The surface area of composite sample was 23 meters square per gram. And the electrical conductivity also shown remarkable improvement from 0.0097 to 5.113 Siemens per centimeter. Then density was as low as 0.021 gram per centimeter cube for the pure sample, and for the composite it was increased slightly to 40 milligram per centimeter cube. Then the main part is shielding performance. The pure sample has shown a maximum shielding efficiency of 17.37 dB in X-band frequency region. Upon polymerization, it was improved to 55.35 dB with a thickness of 3 mm. And in KU band, it was further improved to 62.38 dB, and in K band, we got 71.15 dB. So and another important parameter is skin depth. The skin depth was 2 mm for the pure sample, and it was improved to 0.5 mm for the composite. And specific shielding efficiency, or the shielding efficiency divided by density, is an important parameter in the case of lightweight shielding materials. We got a high specific shielding effectiveness, and a more normalized parameter is specific shielding efficiency per thickness, which has shown nearly 6,000 dB centimeter square per gram in K band. And possible shielding mechanism is shown here, and the comparison study shows our sample VP-HTH has an excellent specific shielding efficiency compared to other reported materials. In conclusion, we could prepare ultra light porous aerogels with high specific shielding efficiency in all 3 frequency regions of X band, KU band, and K band. So this is my acknowledgements. Thank you.
Thank you, Avarna. Any questions from the audience? Any questions from the audience? Avarna, what was the temperature you used for the hydrothermal synthesis?
140 degrees, sir. 140 degree.
140 degree. Then duration?
24 hours.
Okay. Okay, is the experiments are repeatable to your satisfaction?
Sir?
Is the experiments are repeatable?
Yes, sir.
Yes, the same image, everything looks similar when you repeat.
Yes, sir.
Okay. Okay, thank you, Avarna.
Thank you, sir.
Now, Naina Devaraj. Naina Devaraj. No, Naina is not present, I think. What about Jindumal Matthew? Jindumal. Hello, am I audible?
Yes, sir, you're audible.
Then I think it is time for the second chance to Jindumol Matthew and Naina Devaraj. If they are
Sir.
present, please come forward for the
So may
presentation.
I think we have one more participant, Tanuja Nizam.
Name, please.
Tanuja Nizam, I think we have one more participant.
Tanuja,
Sub 283, Tanuja Nizam.
number, please.
Sub 283.
I think it is not included in this session.
So I think she's present.
I think.
I just think she's present.
Yes, ma'am, I'm present here for the presentation.
What's your name? Your name, please?
Tanuja Nizam.
But it is not given in the list, I think. Okay.
I think it was edited later, sir.
Edited later. So if you belongs to this session.
Yes, sir, I belong to this session.
Energy materials, other materials.
To other materials.
Other materials.
Yes.
So if you belongs to this one, you can start your presentation.
Thank you. Sir, sir.
Yes.
Yeah, this is added at a later stage, sub 283, because she requested.
Okay, no issue. Then you please confirm whether Jindumon and their presentation or not.
Okay, is she there? Or?
Okay, Tanuja, you can start now.
Thank you, sir. Thank you. Okay, the topic of my presentation is removal of chromium ions from aqueous solution using magnesium ferrite nanoparticles. I'm doing research under the guidance of Dr. Renjua Krishnan from St. Xavier's College. We know how crucial is the role of water in the life on Earth, but various unscientific human activities like the discharging of industrial effluents into water bodies without adequate treatment have produced an increase in the contamination of water. One among such contaminants is the heavy metal ions. Heavy metals are elements with atomic weights above 63.5 and having relatively high density and specific gravity. Exposure to heavy metal ions in a level greater than the permitted limits can cause various damage to living beings. Some of the heavy metal ions are copper, cadmium, mercury, chromium, etc. And chromium-6 is one of the highly toxic heavy metal ion. Various techniques, including adsorption, which is an effective method with preferred properties such as low cost and high metal binding capacity, is there for the removal of heavy metal ions like chromium-6 from its aqueous solution. Adsorption is the adhesion of atoms, ions, or molecules from a gas, liquid, or dissolved solid into a surface, thereby creating a film on the adsorbate on the surface of the adsorbent through physical or chemical bonds. The major disadvantage in using conventional adsorbents like activated carbon, clay, etc. for the removal of heavy metal ions from water is the difficulty of their separation from the adsorption site after adsorption. There comes the importance of using magnetic adsorbents like iron and iron minerals like ferrites. Here, the heavy metal ions, that is the adsorbate, together with the magnetic nanoparticles, which is the adsorbent, that is the surface to which the ions are adsorbed, can be easily separated from the water by an external magnetic field. The objectives of this study is the synthesis of magnesium ferrite nanoparticles using sol-gel technique, its structural and morphological characterization using XRD and SEM, and carrying out batch adsorption studies for optimizing various adsorption parameters. Coming to the preparation of ferrites. The precursors, the iron nitrate and magnesium nitrate, were taken in 2:1 molar ratio and was added dropwise to citric acid, which is acting as the fuel. The solution was then dried at 100 degrees Celsius to a fluffy gel and was annealed at 400 degrees Celsius to obtain magnesium ferrite nanoparticles. Then coming to exardic characterization. Exardic characterization was carried out and it was found that spinel type magnesium ferrite with cubic symmetry was formed. Various features of the synthesized ferrite were calculated using using these relations as shown in the figure, like grain size, strain, lattice parameters, interplanar distance, etc. Then SEM characterization was carried out. Samples contained aggregation of the particles due to its magnetic behavior. Now, the adsorption studies. The effect of the adsorption parameters like adsorbent dose, contact time, and initial ion concentration on the removal of chromium-6 ions was studied by batch adsorption studies. Synthetic wastewater containing chromium-6 ions were prepared by dissolving potassium dichromate in distilled water. To 20 milli of wastewater, desired amount of adsorbent was added and agitated for a specific time. And after magnetic separation, concentration of the metal ions in the supernatant was determined using atomic adsorption spectrophotometer. The percentage removal of the chromium and adsorption capacity was estimated using the equations given. The effect of adsorbent dosage. The effect of adsorbent dosage on percentage removal of chromium ions was studied by varying the dosage from 0.05 to 2 gram. As we can see in the graph, there is a sharp increase in the adsorption efficiency initially, then the rate was slowed down. On further increment of the dosage, there is no further increase in the percentage removal. Only a slight increase is visible. This trend can be explained as with the increase in the adsorbent dosage, there is an increase in the surface area and thereby the number of available active sites. But at higher dosages, the nanoparticles agglomerate together, leading to a decrease in the surface area to volume ratio and thereby decreasing the absorption efficiency. Now, the effect of contact time. The adsorption efficiency was studied as a function of time from 5 minutes to 120 minutes. The rate of adsorption increased rapidly in the first few minutes because of the availability of large number of active sites. The rate of adsorption attained equilibrium within 60 minutes and no further adsorption was a slight increase in the adsorption was observed after equilibrium. This can be due to the repulsive forces between the heavy metal ions on the adsorbent surface and the remaining ions in the solution. Now, the effect of initial ion concentration. The variation of adsorption efficiency with change in initial ion concentration was studied at concentrations from 10 to 50 ppm. Adsorption efficiency was observed to decrease continuously with increase in initial ion concentration, and this can be due to the decrease in number of active sites on the adsorbent surface at higher initial concentration and increase in the number of ions competing for the available binding sites. And coming to conclusion, as magnesium ferrite nanoparticles were synthesized successfully using sol gel technique, and its characterizations was done by XRD and SEM. The effect of adsorbent dose, contact time, and initial ion concentration was studied, and it was found that the adsorption efficiency was increasing with increase in the adsorbent dosage and contact time, and it was decreasing with increase in the initial ion concentration. And it is concluded that magnesium ferrite nanoparticles are effective, economical, and promising candidates for the removal of chromium ions from wastewater. Thank you.
Thank you, Tanuja, for the nice and brief presentation. Any questions from the audience? If not, let us conclude the session.
Thank you, sir.
I thank all the participants who presented their research findings in a brief manner here, and also to the organizers of this seminar, this conference, for giving me an opportunity to chair this session on other materials. Thank you. Thank you.
Okay, sir, thank you. Our session for today has come to an end. My sincere thanks to Honorable Chair Professor Syriac Joseph for conducting the session. A great thank you to all the oral presenters for their wonderful presentations. We have all had a great, amazing and rewarding time today with all the amazing talks and presentations. We appreciate the efforts of all who have been a part of this event today. Before we end this meeting, I would like to give a few details about tomorrow's session. Tomorrow, we have 3 parallel sessions of oral presentations on the topics photonic materials and devices, energy materials, and other materials, starting at 9:30 a.m. The session will end at 12:30 p.m., followed by the poster presentations. We then move on to the 5th session of ICMPMA on the topic biomaterials. It will start at 2 p.m. and end at 4:10 p.m. Before leaving, we request you all to fill the feedback form available on the chat box. I hope everyone has had a great time. Good evening and thank you to all. Have a nice day.
Thank you.
Sorry, we do not have a feedback link for the oral presentations. The meeting has ended. You all can leave. Thank you.